Okay, so our next speaker is Heike Vallery. She received her degree in mechanical engineering from Aachen University in 2004 and PhD from TU München in 2009. After spending some time at ETH Zurich and Khalifa University in Abu Dhabi, Heike got appointed and is today a full professor at TU Delft. And since November 2019, she also holds a honorary professorship at the Department of Rehabilitation Medicine at Erasmus MC in Rotterdam. Her work is focused on minimalistic and unconventional concepts to support human gait and balance. And recently, she received Alexander von Humboldt Professorship, and she will return to Aachen. So please join me in welcoming Professor Heike. Heike, the floor is yours.
Thank you very much. Well, I was asked today to speak about body weight support, so I tried to make a summary of what we did, but in a way that it's interesting in terms of drawing conclusions for how to design such systems. And I'd like to start, if this works. Yeah, here's a few examples of devices that we built over the years. In 2012, for example, well, you might not call this a body weight support system, but it basically does that for rodents, first with it for rats, later for mice, and it's meant to investigate recovery after spinal cord injury. It was built for neurobiologist Gregor Cotin and this group. Here's another device, well, just a sketch of it on the bottom left of a treadmill-based system, and then we built multiple overground systems, particularly the float, top right, and the Ryzen, bottom right, which do very similar things. And I'll try and structure my talk around the forces that you actually apply to a person during walking, because that's all a body weight support system does. It applies one single force vector to the person through this harness. And now you can say, as an engineer, you will already tend to start decomposing this force into three components. And that's also how I will structure the talk. And I'll start with the vertical force component. So what do we know about forces that you apply to a person in vertical direction during gait? And Salil Apte, he was a very good master student and then kept on working with us for a while. He did a very interesting review on what effect body weight support has on gait kinematics. So that was basically just a meta study of all the existing findings. And what he found wasn't that surprising. It basically confirmed what therapists more or less already knew, namely up to about 30% body weight support, you don't have that much change of your gait kinematics when you apply vertical forces. But of course, you still have a little bit of change. Now the question is, how can you keep the environment as close as possible to the actual task that you want to train? So if you want to train walking and you're forced to give a little bit of body weight support because otherwise the person wouldn't be capable of training, how can you make sure that this training still resembles the task that they want to execute later, which is walking without body weight support? Okay, so we went further in this direction, and one of the, let's say, intuitive statements that people agree on is that if you want to disturb gait as little as possible and you're forced to take a little bit of weight away because the person is otherwise too weak to walk, then you would at least try and make this force perfectly constant, because you're taking away part of gravity. Gravity is constant, so also this partial compensation should be constant. Well, this paradigm actually makes it a lot more difficult to build a device, because everyone who has ever tried to build a constant force device knows that it is difficult to do with passive systems, and you quickly resort to something that's actively controlled. Now, one of the first things to ask is this paradigm actually true? Do we really need constant force, or can we relax this requirement and build something more simple? So Salil, again, did an analysis of this now using simulations. And what he tried to do was simulate the three most basic principles for unloading. One is a constant force on the left, which is something that would mostly be done with an active system that controls that force. A counterweight system where you have somewhere in the room a partial unloading through an additional mass, or a spring, in which case, of course, you have to choose the zero length, which will determine how much load you take away, and the spring, which will stiffness of the spring. And the question is, which of these environments keeps gait as similar as possible to gait without unloading, even though you're forced to take away this portion U of your weight? And what Salil found, which I think is surprising to many probably, is that the constant force does not perform best in terms of keeping gait dynamically similar to walking without unloading. What is not surprising is that the counterweight is even worse. So you just add more inertia, so you make gait even less similar. But what is, at least in simulations, seems to be the best choice is to use a spring. So instead of a constant force, you use a spring. Well, it wasn't completely surprising to us, because we had formed the hypothesis that if you take away part of gravity, you still leave all of inertia of your body. So that changes the eigenfrequency of your pendulum, basically. And we thought that, well, basically you would like to keep that eigenfrequency constant to have a more or less similar gait. And if you take a spring, you can again increase the frequency of your oscillator. And of course, you would choose that spring to have a spring constant that facilitates this. And that's also what Salil did in the study. He optimized the spring to give the system the same eigenfrequency as it would have without unloading. Well, this is a very nice finding, because it means that we can use much simpler design principles to build springs than we would need to realize a constant force. We unfortunately don't really have an experimental proof of this yet, but we have some experimental indication that confirms this, which we did in a different context. 12 years ago, we tried and make walking with a locomat a little bit more transparent. And one of the things that you have to do when you walk in this exoskeleton, which is a treadmill base, is you have to move the entire locomat frame up and down each time that you take a step, at least if you don't walk at a constant height with your pelvis. And it means that you have to move this entire frame up and down and compensate for both gravitational and inertial forces of it. Well, the gravitational forces are, of course, already taken away, because there was a spring mechanism designed back then that would more or less make the frame free floating. So it would be a more or less perfect constant force compensating the weight of this frame. But we noticed that if you move this frame up and down, you have this enormous extra inertia. Actually, there's about 75 kilograms, the entire thing that you move up and down. So it's a considerable amount of extra inertia that you need to move up and down. And we had this same assumption that we can probably do a better job than constant force by using a spring that exploits the fact that if you walk, then you more or less have well, at least you have a periodic gait, and by approximation, you could say it's sinusoidal. And in a sinusoidal pattern, your acceleration is proportional to position. So you could generate acceleration compensating forces by making them just proportional to position, which is nothing else but a spring, a position-dependent force. And if you tune the spring to have a stiffness that favors a particular frequency in combination with the mass of the system, you would basically make the entire frame an oscillator that oscillates next to you while you walk without having to exchange any forces with it. And that was the entire idea here. Of course, you might say that if you have a slightly different gait frequency, this won't work anymore. Or if you don't have a sinusoidal pattern, but you have more of an asymmetric walking pattern, it might not work anymore. But we did some calculations on this, and we found that this is actually very robust to deviations in gait frequency and also to non-sinusoidal patterns. And then we tried and tested this, but this was only with 3 healthy subjects. But here you already see a pretty large effect. We measured the ground reaction force in the treadmill, which reflects the extra inertia that you constantly have to accelerate upwards and downwards. And of course, we would like the system to behave as if there was no robot. So the no robot condition is the ideal, which is when people were just freely walking on the treadmill. If we now suspend the robot with a constant force, which was the original design, you see that you get a lot more ground reaction forces. So people hit the treadmill a lot harder because they have to accelerate this entire robot mass up and down. And if we do the spring suspension, we get closer to the no robot condition. And this effect is even more pronounced when you walk faster, of course. So that's, of course, this is no proof. This is just 3 people, and this isn't really a body weight support condition, but it's something very similar. So we were very convinced that this is actually a better solution than a constant force control. And that's what we already used for the design of the Ryzen. The Ryzen is a 3D bodyweight support system that was built by Motec in collaboration with TU Delft and Lausanne, again, Grégoire Coutin's group. And well, you can see here some things that the robot can do, but the most important question is how it was designed. And in this case, we chose to have very low bandwidth actuation in the vertical degree of freedom and to rely mostly on these huge springs that you see here on the left. So those springs in combination with very low power motors actually do the job of vertical force control by basically giving it a spring-like behavior. Of course, we still need the motors for usability. You can move upstairs or downstairs. You can sit down and do these kinds of things. And these springs also have a second function, which is, of course, to catch you when you fall, which the motors don't need to do. So these types of fast movements are not done by the motors. So this allows us to build a very low power system, relying mostly on these passive dynamics. Oh, yeah, well, we even built a system that was even more simple, which is what we call the bungee, and it translates a vertical motion into horizontal motion, while at the same time giving you some sort of oscillatory behavior in vertical direction. And all this is just a combination of a spring and a freewheel, and in this case, a chain. So we built this with like 20 euro components from a Dutch bicycle shop. And at that time, we still thought it would be necessary to pull people forward. So that's why we created this transmission from vertical motion into forward propelling. This never became a system. This just remained a prototype. I think it's interesting to see. Okay, I'll go on to the next direction, lateral forces. What do we need to do with directions in mediolateral direction? So this also started with a surprise because in 2010, we did a study with body weight support on the treadmill, but we weren't really interested in the body weight support. We were interested in the effect of inertia on gait. So we added additional diving masses on persons, and we wanted to have a pure inertia. So we thought, oh, we'll just compensate this weight of the diving weights with the body weight support system on a treadmill. But then when we analyzed the data, we noticed that the effect of the diving masses themselves or of their inertia was very small, but what was a lot bigger was the effect of the body weight support system, which we had neglected at first. And we noticed that it substantially influenced people's balance behavior, or at least it changed their step width. And Keith Gordon's group did a similar experiment, and they also noticed some effects of this constraint, this lateral constraint of a standard body weight support system with just a single attachment point at the ceiling on your gait. And they noticed that this constraint influences the balance tasks. So if you want to train balance as realistically as possible, the hypothesis now is that you would avoid this constraint and somehow allow lateral motion. So, for example, we built this extension to a treadmill-based body weight support system that enable you to move laterally without the system resisting it. And we also did a similar thing in the Ryzen. We built in an additional small actuator here, but it's mostly a passive element, namely this strangely shaped winch. And if you move laterally, this winch will move and it will change the lever arm that each of these cables has on itself. Or here's a simulation that Michiel made. You see how the person is walking left and right, and then these cables change just passively. They change their lever arm on this winch, and since the side with the large force always has a smaller radius, and the side with the small force always has a large radius, the moment of both sides more or less cancels out. So you could even build this completely passively. You wouldn't need a motor, but we put in a motor because we can then also compensate for some friction and also apply, if we want to, extra forces on the person, for example, for perturbations. Okay, and the last degree of freedom, longitudinal forces. What do we know about those? We recently did a longer study with the Ryzen, and we know that the Ryzen is pretty transparent, so we can very clearly know which forces we're actually rendering on the person. And we noticed, surprisingly, that you don't really need forward force to keep walking at the same speed, even though you get unloaded. So this is for healthy subjects and their self-selected walking speed for certain types of unloading. But they, and we gave them zero force in forward-backward direction. And we noticed that, well, their speed doesn't really change. It's still more or less the same regardless of the unloading. So that was surprising and not what we had expected. We thought we would have to pull people forward the more we unload them, but that isn't really the case. And what is even more surprising is that people don't like being pulled forward. So we added a condition where we asked people to just select the force that they wanted. First, we did that with 15 healthy subjects with 30% of unloading. And interestingly, they all selected negative forces. So they all wanted to be pulled backwards slightly, which is counterintuitive because that increases metabolic cost. You would expect them to want to be pulled forward so that walking gets easier, but that's not the case. There seem to be other optimization criteria that people prioritize over metabolic cost. And with then we had 3 patients, of course, a very small number. So this is definitely something to do with more people. And we asked them and the therapist to tell us what would be the best AP force for them. And we saw, well, very small forces, but no consistent pattern in forward or backward direction. So it doesn't look like we really need a forward force. Okay, what we did find was another huge surprise, namely that harness attachment is much more important than we thought. We had a harness attached in extreme configurations, only at the back, only at the front, in both sides, more or less equally, and then looped so that this could just loop through a ring up here so that the force would always be identical at the front and back. And we noticed that if you try to get the same walking velocity with unloading as you have without unloading, then the AP force needed to do that actually depends very strongly on the harness attachment. So if you attach the harness only at the front, which is equivalent to the therapist accidentally tightening the straps a lot more at the front, then you get a really high AP force that you need to get to the same speed. And likewise, if you attach the harness only at the back, you need to pull the person back a lot to get the same walking speed. So that was, to us, it was very surprising how large this effect is and how important it is to either keep both straps very carefully tightened identically or to just add another degree of freedom here that allows the system to adjust those forces by itself, which many systems do. They have this kind of loop through thing. But that also means that reporting on the harness attachment is something that's important in studies, and that's regularly not done. Okay, so quite a lot of things that we hadn't expected first. I'll summarize the main effects that we saw. In vertical direction, it seems like this hypothesis that you need a constant vertical force isn't really true. And it might actually make things worse if you keep the force constant. And you can make things a lot easier and probably even better if you have more of a spring-like support. It's also a lot easier to build. In lateral directions, well, a lot more research is of course still necessary, but it seems like if you constrain a person in lateral direction, it affects the balance task. So if you don't want it to be affected, then probably you would like to give lateral freedom in the device. In the longitudinal direction, anterior, posterior, surprisingly, positive forces aren't really necessary, and people even prefer or seem to prefer to be pulled slightly backwards. So this is very nice because that is easy to realize with a system that's not actuated and just has some intrinsic resistance that you can't avoid anyways. So this can also further simplify designs of these devices. And the interesting and related finding is that harness attachment really has a huge influence on how people behave in the longitudinal direction. Okay, but all of this is based on steady state walking and mostly healthy subjects. And this is really not what body weight support is about in clinical practice. Here's an example from a study, not a study, just therapy in Switzerland at Affolter und Albis, pediatric therapy. And you notice how it's really critical to give this additional freedom to the person and to give creativity to therapists who can then allow their clients to explore their abilities. Okay, with this, I would like to close and thank you very much. Are there any questions?
Thank you, Heike. These are surprising results, indeed. Are there any questions in the room or online? Well, I wanted to ask, so you did all this, so you showed that where you attach the harness makes a difference, and you look at forces in all different directions. But ultimately, patients are asymmetric, right? And you have one point of attachment of the harness above them. So do you think the results would be similar if you had two and you could independently control both sides?
So you mean you have both shoulders attached to a different side, to a different system or different?
Well,
probably.
if a patient needs different support to different sides.
Yeah, I know that in the Locomat, in the very old design of the Locolift, they had built the Locolift such that it could have side-dependent support. But they noticed that therapists never made use of it. So possibly something that could be done now with more adaptive controllers that identify which support the person needs on which side. Don't necessarily have to modify the mechanical design for it, probably, because you can still use a single attachment point and give different support to both legs. So definitely something to investigate. There's a lot to be explored still.
Okay. Questions? No, okay. So we are running late already. So let's thank Heike for her talk.